So again, we consider a two-dimensional Gaussian model for a scalar field, phi of x. It's a scalar field, the dimension is still of the theory. X mu is the Euclidean coordinate of x1, x2, and d mu is the Euclidean gradient, d dx1, d dx2, and so forth. All right. It is clear that if we make a scale transformation of the coordinates, then this measure will acquire lambda squared, and this gradient square will acquire 1 over lambda squared. These two will cancel, and the whole action will become scale invariant without any need to rescale the field. Which means that under rescaling, the field goes to itself. It's a true scalar field which is not being transformed on the scale transformation. Right? Then we conclude that the scaling dimension of such field is 0. And the question is how the correlation function, gamma of r, phi x1, phi x2, how does it behave as a function of the distance if the scaling dimension is this? Now, what we have defined, that's a definition, that if we have a field phi, which under scale transformation transforms like this, then we know how the correlation function gamma of r should behave. Why do we know that? How do we know that? We simply produce this scale transformation for the correlation function now. This means that inside the averaging, each field will be scale transformed. Under each scale transformation, we'll get out this prefactor, so altogether it will give you this one. And then it will go to gamma r, right? So this is the scale transformation law for the correlation function once you know the transformation for the constituent fields of which this correlation function is bigger. Right? Now the trick is, the lambda is an arbitrary parameter. If you choose lambda to be 1 over r, in the left-hand side you get just a constant, gamma 1, which is a number. Here you have r 1 over r to the power 2 delta, and here we have gamma of r. Altogether you find the answer. Gamma of r is some constant divided to the r to the power 2 delta. That's the proof. So if you know, again, if you know the scale transformation law for the field, then it automatically follows that the correlation function, the two-point correlation function of this field, first, must be a homogeneous function. That means that it's a polynomial function. It's an algebraic function. And the degree and the exponent is twice the scaling dimension of the field itself. Now the question is, what happens, like here, when delta goes to 0? When something goes to 0, you don't know the answer. The natural reaction of any consistent scientist would be, let me imagine a situation when this dimension is a continuous parameter, can be varied continuously, and becomes infinitesimally small, but still finite. So let me follow the way it goes to 0. So therefore, we are discussing the situation with the behavior of the correlation function, gamma of R, which is of this kind. This is all what we can do. A little better thing would be to replace this by something already normalized in such a way that what we have here is a dimensionless quantity and R naught is some microscopic scale, which can always be achieved just for normalization. Now what you do is the following thing. Well, of course, everything can be multiplied by some coefficient. This constant here, some coefficient, which may depend on epsilon. In principle, let's just be quite generous. The only thing I did here two things. First, I made the length dimensionless. I measured the length in units of some minimal length, better spacing, suppose. Secondly, I multiply this correlation function. Well, it's not still equal. It's a behavior at distances are much greater than R naught. Please don't be confused. Maybe I was not quite consistent in not stressing this circumstance every time. It's very important. When we talk about, when we produce coarse graining, just go back in your memories to what we've done. And we have replaced our microscopic variables like Ising variables, Ising speeds, or three-dimensional speeds, classical or quantum, doesn't matter, by some fields. If we had replaced this by fields, and the coordinate on which the field depends is just the result of this cold grain procedure. So the center of gravity, the center of this bubble, if you wish, of some radius L, which is much greater than interatomic distance, but much smaller than the correlation length. So this is why we define the physical point. By the way, it must be known to you from the standard courses of theoretical physics. What is the difference between the mathematical point and the physical point? The mathematical point doesn't have any dimension. It's just dimension 0. Because anything which has the dimension, the minimal dimension is 1, it is line. Now in physics, a point does not mean the mathematical point. It's always a coarse-grained object. It always has some extension, some spread. In quantum mechanics, that will be an extension of the typical size of the wave function, and the wave function cannot be a delta function because of the uncertainty principle. You name all the reasons which follow. So here, for us, the physical point is the point which emerges as a result of coarse grain. So we take one point, we take another point. It's absolutely clear that any distance between two physical points, coarse grain points, must be much, much larger than the minimal interatomic scale over which we have already averaged when we created a physical point. Right? This small distance doesn't exist anymore. So therefore, if R naught is some minimal scale, this is just the asymptotics. It is not a function which is valid at any distances. It is only the long wavelength distance limit. It is what the most interesting physics is about. Very large distances, very small momenta, very low energies. Okay, so when looking at this, what we do, let us rewrite it in the following way. All right? Right. Now let us assume that epsilon is small. Correct? Correct. Now what do we want to achieve? We want to achieve one thing. We want to find out, is there any dependence on the distance which survives the limit epsilon goes to 0? The first sensible thing which emerges in this discussion is this logarithm. But it has in front this coefficient epsilon. For the logarithm to survive, we have to insist that a small epsilon, c of epsilon, behaves as 1 over epsilon. Then what you can find out, this goes to 1 over epsilon, plus some constant, c naught, this time doesn't depend on epsilon already, times the logarithm, times the correction of the first order of epsilon, which can be discarded, in the limit when epsilon goes to 0. So your problem is only the first term, which is formally divergent. But you know how divergences are treated in condensed matter physics. The answer is there should be no divergences whatsoever. There may be large quantities defined by very short distances. So therefore, here I come back to the idea of coarse grading. How did I perform all that? Maybe there are some remnants, some residual things remaining in our discussion. It is just this, at that very point, you need to go to your original model. The original model, I call it here, is a scale invariant action describing the two-dimensional Gaussian model. And just for this model, you have to diagonalize the action, you have to calculate the correlation function, phi of x, this correlation function, gamma, which is phi of r, phi 0, using this expression for the action. You know how to do path integral for the Gaussian model. We have done it already when we considered the Ornstein-Zernicke formula for the correlations in the Landau-Giesberg theory, remember? And then you will find out that you will get something like a two-dimensional logarithm which would emerge as a result of this kind of integration. Times, of course, this running Fourier exponent, because I have to translate this integral into a coordinate dependence on the correlation function. But then the question is about regularization. This integral is log divergent at short distances. Please notice what I've done. I have somehow by hand introduced this cutoff. Just out of the blue, I would say, without any derivation. So what you can now do, you have the idea that there should be a logarithm, because this is the only conceivable function emerging in the limit when epsilon goes to 0. What is the feature of this logarithm? When you make a scale transformation, logarithm doesn't get renormalized multiplicatively. It doesn't acquire any prefactor. Instead, if you make a transformation x to lambda x, the log of x goes to log of x plus log of lambda. There is no multiplication. It's only an additive piece which emerges. So it's a kind of breakdown of your concept. You started with the assumption that all correlation functions get multiplied. This is what scale invariance is about. So you see that if the only thing which is conceivable with the statement that for the operator with the zero dimensionality, the only conceivable function is a logarithm, but the logarithm does not fit the standard scheme, and therefore, per se, this function phi of x cannot describe physics. It is a right result, the right result for this theory. But the field phi itself cannot be a physical field. What can be a physical field? Its derivative. Because the derivative will immediately transform your logarithm into a power law. Or it turns out it's some kind of exponent. And now we are coming to very deep things systematically discussed and described in the so-called conformal field theory, which is completely beyond the standard course within the diploma program. So therefore, we will have an example of this kind, but a little bit later. In the last 2-3 lectures, all this kind, give you a few more examples of this kind. So at least the answer is the only conceivable function is a log, but the log breaks the scale invariance in the standard sense. Under scale transformation, the log acquires a constant, but you call, well, there is a good excuse, you know, every time physicists deal with logarithms, the logarithm is never well defined. You can specify some point for which you measure it. So to write down log of x or log of x minus log of x naught simply means that you start measuring your coordinate in different units. Scale transformation of the coordinate gives you an extra piece. So therefore, the extra piece is not due to some deep physics. It's due to the way you treat the function. All right, so it is not a very simple thing to solve, but it's a good example for you to understand. So zero scale dimensionality. If the function, if the field has zero dimension, its correlation function is necessarily the log. All right, not the problem. All right, so much for this case, but now we are coming to a more interesting situation. So this is an example. This is an example of a scale invariant action, and therefore this is a fixed point action. Because at the fixed point, you remember, the fixed point action is the action which, by definition of the scale transformation, doesn't change its form, which is scale invariant. Now imagine then in your memory what the Ising model was about. The Ising model was about the following action. It was the integral over d-dimensional space. Here we have a gradient term, which I will write down something like d mu phi. So it's an Ising-like story. Phi is a scalar field which mimics the spin, the Ising spin. And then we had the term which was quadratic in this field. And we also remember that A, according to Landau theory, was proportional to the distance from the critical point. T minus Tc tells us T minus Tc by Tc. The distance on the energy scale, the temperature scale, right? And on top of that, there was a fourth order term, which was needed because otherwise we would not get to the spontaneously broken phase. Right? But to us, if you are at criticality, now why are we saying we should be at criticality? Because we want to discuss whether or not any model like this may be scale invariant at criticality, because away from criticality, scale invariance doesn't hold, it doesn't exist, right? So therefore we skip this term because we set tau equal to 0. And what remains is, let me now change the notation and write down something like 1/4, if you wish, g squared phi to the 4th of x. All right. Previously it was 1/4 of b, and b positive. So to emphasize that the b is positive, I replaced b by g squared. So it is obviously a non-Gaussian model. Because in the Gaussian model here, phi would be squared. It's 4th. It's phi to the 4th. This model is not Gaussian. The question is, can such model be scale invariant? Can such model describe a critical point belonging to the Ising universality? And we will now see how beautiful is the answer to this question. You wanted to say something, or you already calculated? You already calculated. All right. So we do two things. Generally speaking, there is no reason to expect that the field phi will not get renormalized. constant. Of course it will. So therefore we change x to x prime, which is lambda x, and correspondingly we change the field by phi prime x prime, which is zeta phi of x. All right, the standard thing which can be assumed in this case. Let's see how the action will change. So this measure will give an extra factor lambda to the power of d. Right? ddx. So therefore the action will transform as follows. It's again the integral over ddx, right? Oh, not prime, x, the same, because x prime is just this one. Here I have 1/2. Oh, yes. Let it be c, it doesn't matter much. Let me choose the units in such a way that I made c equal to 1. I don't want to do it. It's always possible. Right, so here I have lambda to the power of d. This is from here. And there is a second derivative. The first derivative squared. So therefore it will be d minus 2. Right? And one more zeta square will come from the fact that there is a field, and here I have d phi squared. What I have here is 1/4 g to the 4 lambda to the power of d coming only from this measure. And from here we have zeta to the 4th. Is it correct what I... Yeah. And nothing else. Right. And nothing else. Phi to the 4th, phi goes to zeta, zeta to the 4th, and lambda d is nothing else. Now the question is, when this construction is identical to what we have started from. Two conditions must be satisfied. Lambda to the power d minus 2 zeta squared must be equal to 1. And secondly, lambda to the power of d zeta 4 must be equal to 1. So from here we conclude that zeta squared is lambda to the power minus d divided by 2. Substituting here we find lambda d minus 2 zeta squared minus d by 2, which gives us lambda d by 2 minus 2, which gives us lambda d minus 4 by 2 must be equal to 1. Conclusion number 1. The last condition fixes the space dimension. D must be equal to 4. The scale invariance is only possible in 4-dimensional space. Now from here we see also that since we know D, then the second is zeta squared is the lambda 1 over lambda squared. In other words, zeta is 1 over lambda. Right? What does it mean? It means that if I have a field lambda x is multiplied by zeta is 1 over lambda phi of x. Correct? But we remember, if we make a scale transformation with the field, what is written here gives us the scaling dimension of this field. So therefore we conclude that the scaling dimension of the field phi is 1. times the power. So, the action that you see here, number one, is scale invariant in 4 dimensions. Not 2, not 3, but 4 dimensions. In 4 dimensions. At the same time, the field scales in such a way that its scaling dimension is clearly 1. Since the scaling dimension is clearly 1, the corresponding correlation function as a function of r decays as r squared. Right? Twice the scaling dimension. Now let us recall what we remember from the mean field theory, from the Ginzburg-Landau mean field theory. In the Ginzburg-Landau mean field theory, the correlation function, gamma of r, is proportional to the d-dimensional integral. I don't write down this 2 pi to the power whatever it is, exponent I chi r, and I'm now looking at the correlation function at criticality. Therefore, this kappa square is absent. The correlation length is infinitely large, and the small kappa, therefore, is 0. You remember, right? So what you have here is the integral, roughly, k d minus 1k, with this to d minus 3k, dk, and the exponent. Now what I do now, it's a typical way how to brutally and roughly estimate the integral. How to squeeze out the main coordinate dependence of this correlation function, even though you don't know how to exactly calculate this integral. You may do it numerically. You may even discover that it requires some regularization. Something has to be subtracted for that, for the result to be finite. Nevertheless, the main result can be anticipated by very simple heuristic arguments. You look at this exponent, and you say, the contribution of integrating over k will give me a reasonable finite result, results until k modulus times r modulus stays of the order of 1 or less than that. If I exceed that, if I go to the limit of larger k's, this exponent starts oscillating rapidly, wildly, and will cancel the contribution. Because you will get cosines and sines. This exponent consists of cosines and sines. Cosine and sine are sign alternating functions. They will have positive contributions, which will be systematically cancelled by negative contributions, and so on and so forth. So therefore, effectively, you can forget about this. But say that the maximum of k is 1 over r, under the condition that the integral is convergent. That's the trick the theoreticians do. There are different stages, several stages. When you start working, first of all, you need to have some impression what you are driving at and what is expected to be seen. This rough estimate must be done quite brutally, quite roughly, but realistically. And this is a realistic argument, actually. So that gives me the maximum k is k to the power of d minus 2, as you can see, right? And therefore the function will behave as r to the power of d minus 2. Now when d is 4, you get 1 over r squared, and that's precisely what we have received, what we have obtained. So therefore, what we have obtained is the correlation function in the Landau-Ginzburg mean field theory, which tells us that this theory is nothing but the Landau-Ginzburg mean field theory, which in 4 dimensions is exact. It does not contain any approximations, so to speak. There will be some corrections to that, and will come in some 20 minutes later. So it's an excellent example. So we already know from independent piece of knowledge that d equal to 4 is the upper critical dimension of the Landau-Ginzburg theory. We know that it is only at d equal 4 and higher dimensions that you can expect mean field theory to be viable, realistic. But exactly at d equal to 4 and not in d equal to 5 to 6 to 7, even though those theories are perfectly described by mean field theories, only at this in this dimension such an action has the fantastic property of being scalar-variant. Completely, both ways. That's amazing. So the theory is not a Gaussian, nevertheless, it is scalar-variant. Which strongly supports the point of view that if you have a potential which is the free energy, it's a function of your phi, and you have symmetric minima, phi naught minus phi naught, right? This is the ordered phase. It is just the Gaussian, that will be a disordered phase, at criticality. At criticality, you simply have phi to the 4th without phi squared contribution. And such theory describes a critical point, but not within any kind of Gaussian model. It's non-Gaussian, nevertheless, it is scalar-variant. Why? Because you are just at the point when the system changes its behavior. You get from one phase to another. It's not simple, it's complicated, people. I understand that you get acquainted to something which doesn't appear every day in textbooks. But it's an important part of your knowledge. I'm not going to introduce you into systematic description of what is called now a renormalization group and the scaling theory, but some flavor of that you have to know. You have to have it. Otherwise you won't be, if you simply would say, okay, well, we had a course on phase transition, our professor taught us mean field theory. Mean field theory is the same as Landau theory. Oh, how nice. If you hear me, you know phase transitions? No, we don't. It's not enough. With all due respect to the great Lev Landau, what he've done was fantastic, but it's not enough. All right. Any questions here? Now we're passing to a very important, very fundamental question, which has to do with perturbations at the fixed point, at the infrared fixed point. So we would like to start with the scalar-variant model, which describes some critical state of the system, and we would like to perturb it. For instance, we have a rising model at criticality, which can be only critical if the external magnetic field is 0, and when the temperature fine-tuned to Tc, so you can two ways to perturb it. Either you go slightly away from criticality by increasing or decreasing the temperature, or you may switch on a magnetic field. In any of these two cases, you lose the critical state. Because I don't need to discuss the original. So, let us assume that we have an action which is a function of some field, or better to say, fields, that's plural. Field, the number of fields may be more than one. The field may be a vector field, they have many components, first of all, and they may be different fields, physically different fields. So I assume that this is a fixed point action, which is scalar-variant, which describes some critical state of the system. But this is not all. I would like to perturb it in the following way. I will add the following terms: lambda n and phi n of x. What are those, first of all, phi n of x? Phi n of x. It's a set of fields. Sometimes people say a set of operators. But operators in statistical physics do not necessarily mean that operator like a differential operator. No, it's a fields. It's fields. They become operators when you compact the theory, but it's a different story. For instance, it can be another parameter, m of x, in the azimuth. It may be its gradient in the azimuth. But it's also maybe what we have, sigma n plus g, when g is the nearest neighbor vector. It's an energy density in the macroscopic Hamiltonian. So in field theory, it's replaced by some epsilon of x, another field, which is basically a product of these two fields with some point splitting. So you at least have already three of them. The field itself, its gradient. This couples to magnetic field, so therefore the corresponding lambda for it will be h, right? I may have something like this. I cannot have this in the first power because that will break parity and rotational invariance, so perhaps I will have terms like this, but if I do break some symmetry, I may have even the same gradient in the first power, in principle. Or I may have may change the temperature, and then the change of the temperature will couple to the energy density. So I have the whole bunch of possibilities, and each of them comes with its own coupling constant. Lambda n is the coupling constant which is conjugate to the corresponding field. The other good question is, if you are here and you add something like this, do such perturbations drive you away from this fixed point? So this is a fixed point actually, right? Is it stable against such perturbations? In other words, if I have a criticality described by this action as stop, how do I know that switching on this or that perturbation, I will stay again within the same criticality, or I will be driven away from it? The system will go to a non-critical state. Maybe along this path meet somewhere another fixed point, which describes either another criticality or another stable situation. We don't know. So what we would like to know is whether or not such a perturbation, as we say, is relevant, is irrelevant, and there is one more possibility, as it's accepted in the theory of phase transition, or it is marginal, somewhere between this and that. So let us recall again what we do when we produce the RG transformation. By the way, did you receive from the ladies the extra notes? You did? Oh no. Because there is a text with a few typos. I found a few of them, much smaller, much less than in the basic text. But there are problems there. So what we basically do in the RG, you remember when we considered the field with some cutoff lambda, and then we change this cutoff from lambda to lambda prime, and we integrated out all this region of momenta. And then equivalently, what we actually found was that amounted to, so if lambda prime was lambda divided by d, that was equivalent to a scale transformation from x to dx. That we know. Now the first thing we can do is to produce such an RG transformation without action, full action. This full action, which consists of the fixed point action plus perturbation, is subject to the RG transformation. Now we know that RG doesn't do anything to this space, so it's scaling there. The question is what happens here. What happens here is the following. You write down this ddx and sum and lambda n. From here, you get this b to the power of d. On the other hand, your field gets rescaled like this. On the other hand, you know that this is the same as delta and 5x. So what I did, I used the relation that phi d of x is b to the power minus delta p of x. This is the definition of this calculation. Right? So you see that lambda n has transformed to some lambda n tito, which is lambda n, and b to the power of d minus delta. Yeah. Delta n perhaps, since if I specified n here, I have to specify delta as well. Yeah, so far so good. But now, there is one thing which we can imagine. We can achieve the following. We can always choose the units of distance in such a way that instead of integrating over ddx, we will simultaneously divide it at the microscopic volume a0 divided by d. In other words, this is actually the d of x divided by a0. This is the dimensionless coordinate. I can always choose such variables that this is achieved. Right? On top of that, I will write down the same. I will only change the notation from lambda to g. I will write down gn. It doesn't matter much. And here I will write down phi n x minus divided by a0. I can always do that. In other words, my only assumption is that I can choose everything in such a way that the length becomes dimensionless. Now, the action has dimension 0. It's dimensionless quantity. Why it is dimensionless quantity? Because S in statistical physics is always beta divided by F, which F divided by T, energy by energy. So it's no dimensions. And the action, remember, in quantum mechanics, action has a dimension of Planck's constant. It's energy times time. It's like it. So therefore, this is dimensionless. This is, I will choose the field to be dimensionless. I can always achieve it. The coordinate is dimensionless. Everything is dimensionless. The whole integral should be dimensionless. Therefore, Gn is dimensionless. It's one. It does not have any dimension. Any engineering dimension doesn't have a dimension of length or velocity or energy or anything else. I can always achieve that. And then I will simply switch back to whatever is written here. Instead of lambda n, I will write down this gn, assuming that I have already divided the x by the corresponding a0, and I measured x in terms of a0 units, and then gn is dimensionless. That's fine. And then I see the following thing, very important thing, which tells me what happens to this gn. To find out what happens to this gn, I can now erase everything here completely. It's just a brief exercise. Let me now produce an infinitesimally small RG transformation. So we remember that x should go to dx, and b is slightly greater than 1. So let's be very, very close to 1. So what I can write down? I can write down is x plus d delta x. X goes out 1 plus delta x divided by x. From here, so I conclude that therefore d is 1 plus delta x divided by x. Is it clear? kind of infinitesimally small RG transformation. The coordinate has to be multiplied by a factor, and this factor is very, very close to 1. It's 1 plus something. So therefore, this is the solution. Now ddx transforms to what? Without any calculation, it's clear it transforms to 1 plus d delta x divided by x. Is it clear? Because you have the power of d and you do a Taylor expansion in small delta x. Looking at you, I can see that you can't fully understand. You do or you do not? Shall I be more specific? A plus y to the power of d at small r is 1 plus dy plus I all the terms.
Yes.
Of course. Right. Now the field. The field should be b to the power minus delta. But b is 1 plus delta x divided by x to the power minus delta. So therefore it is times phi n of x. So therefore again it is 1 minus delta n delta x over x phi n of x. Everywhere I drop the quadratic corrections in delta x. For the same reason. Instead of d I have minus delta. The same reason. So therefore, if I do everything now correctly, if I collect all the terms, and what I need to collect here, I will have basically collect the product of this integration measure, ddx, and the field. And that will give me a product of this times that. This times that. In the linear term with delta x over x, I will come up with the following expression. Gn will be replaced by Gn prime, which is 1 plus d minus delta n delta x divided by x Gn. Is it clear? It's straightforward, right? So if I take this first term here, I'll bring it to the left-hand side, I will get the difference Gn prime minus Gn, which is delta Gn. And the change of Gn, the change of coupling constant, turns out to be like this. So, this delta x by x actually gives me just the spirit of what's going on to the distance on the DRG. The object which emerges here in the right-hand side times Gn, by the way. I'm sorry, times Gn. This applies to any distance, including the lattice spacing A. The cutoff, R0, or A. Right? So therefore, what I can do is to write down the following equation. And then make a most important step in this logic. I will assume that I can pass to the continuum level. In other words, when I write down x is b to x, b becomes a continuous variable, continuous parameter, which varies from 1 and can all be a little bit increased. And this increase may be described in terms of differentials. That's the only thing I'm doing. Therefore, what is written here transforms to the following equation, which is worth to be written separately and clearly. D Gn d log of A is equal to d minus delta n Gn. What you see here is no more nor less but that very famous RG equation, normalization equation, for the dimensionless coupling GM. If you were in the high energy section, I would say this is the Gelman-Lowe equation for the invariant charge G. The G's are called the charges, proudly. We say coupling constants. The essence is just the same. The variable is logarithmic. It's a logarithm of the distance. Don't be upset. When I write down A, the logarithm of the dimensionless can only exist if its argument is dimensionless. Therefore, I always assume I can divide A by some normalizing factor. A divided by A. But A is a running variable. You remember what was happening? The sequence of RG transformation was from R0 to R1 to R2 to R3 and so forth, where R of K will be B to the power of K R0. You remember, the larger and larger and larger scales. And every time you do that, you look what happens to the coupling constant when you increase the length scale. This only makes sense when the correlation length is huge. Right? So you're still within a subcritical or critical regime. Yeah. Now, this is not the most general form of these RG equations. First of all, the question number one is, how do I know if in case I have many coupling constants, that the equation for the given coupling constant is closed? Why the right-hand side does not depend on some other coupling constant? Generally speaking, it does. A more general RG equation would look as follows. Here I would write down the so-called beta function. In field theory, it is called the Gelman-Lowe function. Gelman-Lowe function, the beta function. This equation, as well as this set of equations, it's a set of so-called autonomous equations. What it means, autonomous equations. The unknown functions are the GNs, the couplings. The variable is the log of A. The right-hand side does not depend on this log. It only depends on this. There are many examples of this kind in mechanics. Maybe this pendulum problem, when the pendulum goes from the upper unstable point and makes a full turn and comes back to this position, and it takes an infinite time for that. If it starts with the zero initial speed, it's a very beautiful problem about the solitons, actually. It's an example of the autonomous equation. Because the potential energy is a cosine. Remember, cosine is the energy in the gravity, in the presence of gravity. Because there is a mass there, right? So, yeah, all right. So, generally speaking, beta n as what? Is a sum over m. There is something like nm gm. Then you may have mk ml d n ml gm gl, and so forth, so on. So generally speaking, this is a matrix. Already in the presence of linear term, this is a matrix which depends on two indices. And here we have a particular case when this matrix is diagonal, when m is equal to n. There is only one coupling constant in the left-hand side, in the right-hand side, which is coincides with that in the left-hand side. And generally speaking, this is an expansion in powers of the weak coupling constant. The coupling constant is assumed to be weak and therefore can be expanded to higher orders. Once this is no zero, you can have good reasons to forget about this correction. But this correction will be decisive if for some reason all coefficients CMM vanish. Then everything starts with the second order, and this is a completely different story. So we will assume, for the first case, just what we have. And what we have is just this one. And from here we observe the following stereotypes, patterns of behavior of all perturbations. So we're looking at the coupling, particular coupling constant Gn. And what we observe is the following, that there is a case, there can be a case where the scaling or corresponding up field phi of n, phi n, scaling dimension must maybe less than the space dimensionality. Anyway, it's a good example of what matters at criticality. I once told you, at criticality, what matters is the symmetry of the order parameter, the symmetry of the problem in general. We are discussing in this case, the simplest case, the phi as a set of scalar fields, or maybe vector fields, but as a derivative of the scalar fields, right? So it's a Z2, it's a discrete symmetry. It might have been a continuous symmetry if we had a vector order parameter. And the second thing, which also fits the concept of universality, is space dimensionality. Only gross features such as symmetry of the order parameter and dimensionality of space matter at criticality. Small, tiny details, what happens at short distances is not important. Nearest neighbors or next to nearest neighbors or even further, as long as the radius of interaction remains finite, these details are unimportant. They only affect C, but not the critical response. And this is an example, so the result depends. It's already hidden, it's already somehow hidden in the structure of this equation that of course we are dealing with. Of course we are dealing with the scalar function phi, and this is an Ising-like situation. The second thing which appears as dimensionality explicitly enters this condition. So if the scaling dimension of the field in question is less than B, you see, the right-hand side here has a positive coefficient. So therefore, where I increase A, if I start increasing the scale of the system, Gn increases. And it will increase all the way. The more is the number of RG transformations, the more will be the increase. And this is the first signature of the fact that this action will not be stable against such perturbation. Because the amplitude, its amplitude effectively increases, goes to infinity, concerning with that. Which immediately indicates that your action is not stable, at least against this perturbation. You lose the stability, your action is unstable, you have found out a weak direction, and the system will start leaking along it and start searching around until it finds another fixed point which is presumably, allegedly, more stable than this one. So this situation determines a relevant perturbation, relevant. There is another situation when delta n is greater than the space dimension. Then the sign is negative, and if you had started with some initial value of G, any further step of Rg will decrease this G. So you started with a finite amplitude of some perturbation, and after a few steps of renormalization, it dies out. You can't see it anymore. Of course, this is a case of irrelevant perturbation. And the case when your original action is stable. There is a third possibility. When delta n is equal to, as you could already anticipate, this is what we call the marginal perturbation. For such perturbation, the right-hand side of this first order equation vanishes. So you again recall this structure. You don't have this term. So therefore, the whole RG procedure starts from the second order terms. And that has to be derived from scratch. So far we didn't have such a possibility. It's a very complicated thing. An example of this kind emerges in the so-called Brzezinski-Kostanista-August transition for thin layers of superconductors or superfluids or XY, two-dimensional XY model, and many more. Now, if you switch on this term, we have to do this analysis once again, all over, because this analysis it's the first order analysis. When this term vanishes, and you have everything starts from G squared. For the second order correction, you have to solve this equation and find out the regimes when the coupling constants go to zero, or the coupling constant increase. So therefore, perturbations here, according to the analysis which we don't perform, can be either marginally relevant or marginally irrelevant. Or they may be marginal exactly if this beta function is identically zero to all orders. So in other words, if this left-hand side, if the equation dg d log a is equal to zero, is exact, simply exact, in all orders, to all orders of dg. But this is a very special situation. Some people claim, especially those who are interested in certain mathematical physics problem, they consider this as a realistic case. Apart from some Gaussian model, I'm not aware of anything else in this respect. So we have all the definitions: relevant, irrelevant, marginal, and we understand that. So you see, the problem is, first and foremost, you write down your model, you write down your situation. So, for instance, you start looking at Ising model, something very simple to imagine, right? The Ising model, of course, has the bunch of exchange coupling constant Gij, nearest neighbors, next to nearest neighbors, whatever, and the magnetic field. All these can be treated as a coupling constants. So what you can do, for instance, you choose the model H star in the following way. Ij, nearest neighbor, sigma I, sigma j. That means that all next to nearest neighbors, next to nearest, blah, 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 are equal to zero. On top of that, age is equal to zero. I know that such a model in dimensions greater than 1 can exhibit a phase transition. I find the transition point with all the nearest neighbor interaction, no magnetic field, no further interactions. I find the TC, I sit at this point, and I'm looking at the behavior of the system. I find out something in the picture. Then I can do this coarse grading, forget about my speeds, introduce scalar fields. It's another story. Everything comes to this one. This is already the Hamiltonian, which gives me a very good idea of what this scalar variation is about. I have to reach criticality here. Then, if I'm lucky and I have good mathematical background, I will come up with the corresponding field theory, which has the same universal properties as this one. Right? Now, let us play the following game. We know that the phase transition disappears at h non-equal to 0, at any finite non-zero h. And we know why. Because the magnetic field explicitly breaks the two symmetry, and the degeneracy between the vacui disappears, and therefore no phase transition takes place. But suppose that h is kept equal to 0. But I add a nearest neighbor, next to nearest neighbor interaction, so this is the model. I add it with those across the barrier, which have not been taken in account here. What, in your opinion, which of the three of these, all this perturbation, this fall In which class will it fall to? Will it be relevant or irrelevant or marginal?
It depends upon the lattices and which lattice D, which we are taking.
Well, suppose the D is such that the transition exists. Take D equal to 2, for instance, a two-dimensional algebra. It is exactly solvable model, and we have a solution for the nearest neighbor model. Suppose I add it by hand next to a nearest neighbor coupling. How do I expect the solution, the famous on-cycle solution, to change? Will the critical exponent change or not? Will we know? Remember, very important, the most important part of the idea is universality. The critical behavior of the system is not determined by what is TC. TC, of course, is sensitive with respect to any microscopic changes. Nearest neighbors or next to nearest neighbors do affect TC. The larger is the coordination number, the higher is TC. Because the less is there are fluctuations of the molecular field. I'm not talking about that. I'm talking about what are the critical exponents you can measure experimentally, calculate theoretically or numerically. Will they change or will they not when I add this? Do I change the dimensionality of space by adding this interaction? I don't. Do I change the symmetry of the system, which was Z2? I don't. Do I change the radius of interaction? Yes, I do. It was only nearest neighbor, now it's next to nearest neighbor. But does the radius of interaction remain finite? Yes, it does. So what do you want? Nothing will change. You will get the same critical behavior as before. So therefore, this perturbation is irrelevant. If you build up a field theory and manage to describe this perturbation in terms of some extra field with the corresponding coupling, this coupling will brilliantly go to zero at much distances. You will start deviating from your fixed point and you beautifully come back to it. There is no way to avoid it. But now play the same game with H. Switch on a small but finite H. And do the same exercise. You don't change the space of degeneracy of the order parameter. You don't change the space dimensionality, but you explicitly break the symmetry. Well, of course it will be relevant, because you lose criticality completely. You are not critical anymore. The third example, you have fixed the temperature, the transition temperature. But temperature is at your disposal. You may change the transition temperature by playing this game. Right? You slightly add a little bit of this and you change the transition temperature. Or you may keep this temperature fixed and you, by hand, the external parameter temperature can be changed. The temperature couples to the energy density. Where is it? I just erased it. Absolute effects. It couples to this tower. Absolute X is one of these operators. If you change the temperature, you simply will shift the transition temperature from one point, from one value to another one. And that's all what you do. You don't do anything else. It will be, of course, it will be marginal. So there are interesting things happening here, and some intuition needs to be developed. But for us, the very simple thing is the following. If we go back to the model we have already discussed, and that was the model, the gauge-invariant model D4X, the four-dimensional model, 1/2. Give me phi squared, plus 1/4 of g squared, y to the 4th. All right? we found out that the scaling dimension of the field phi was 1. Did we? Was it 1 or? 1. Right. This is for the field phi. For the field u mu phi, what will be the scaling dimension of delta u mu phi? I'm waiting for your response. You know the dimension for phi. What is the dimension for u mu phi then? If you know this. No calculations, that's just common sense. You differentiate the field once, right? You send one more x into denominator. It will be d phi plus 1, it will be 2. Right. What will be the scaling dimension of d mu phi squared? Yes. It is 4. What is the dimension of this of the action, the spatial dimension? It's 4. So the dimension of this operator coincides with the dimension of space. This is this case. Conclusion. If you have an action which is suspected to be a scalar invariant action, this which is one of the most important one, the gradient, can only be marginal. By definition, its scaling dimension should coincide with this one. But since this is the property of the whole action, we can say precisely the same about phi to the 4th. And this is quite consistent because you know the dimension of phi is 1, so the dimension of phi to the 4 will be 4. And now it turns out that this and that have the same scaling dimension. They have, all of them are 4-dimensional. This for dimensionality of the operator, so the fields coincide with the space dimensionality. So therefore, the whole action is marginal. Now look, this is a Gaussian field theory. What can be produced, and you know the behavior of the correlation function of these fields of the phi to phi. Would you expect when you build up corrections in powers of G? And this has been done many, many years ago by a group of very talented physicists, which they found out that indeed, we know the result. In 4 dimensions, we have to have Ginzburg-Landau to be an exact approach. The mean field does work, but there may be corrections. The only corrections which are allowed are, in this case, are logarithmic. You can think about that and find out why logarithmic and nothing else. So, this is the end of our brief introduction into scaling, renormalization, and the idea of scalar invariance. And the very fact that different fields at criticality do exhibit scalar invariant properties, but the behavior, the asymptotics of the critical exponents deeply are rooted in the structure of the theory, and if we write down something like this doesn't mean that we have solved this problem. We have not. We can easily solve only the 2-dimensional problem with the gradient term and G is equal to 0 that we have discussed. We described very briefly. And we will have it, just starting from maybe not Monday, maybe it will be the lecture number 11 or 12. So, but we understand where it comes from, and when we know all the story comes from, all these critical exponents which are not captured by the mean field theory are rooted into the scale transformation properties of the constituent physical fields and the constructions that follow from them. To establish this critical exponent is a very, very complicated problem even today. This has been done only in 2 dimensions, just because the scale invariance in 2 dimensions transformed into what is called the conformal invariance. Scale invariance adds It's invariance under global. When you stretch your system, you change the scale, or you squeeze your system. You do everything you do is uniform. This transformation does not depend on the location and space. That you must stretch at some point stronger than at other point. So this stretching of your sample will be inhomogeneous. In other words, if I go from this picture to this picture, it's clear what I've done. I have increased linear size, homogeneity, everywhere. But I can do it in the following way. This is not the same. So this is an extra transformation, the extra symmetry, which requires that the angles should be conserved. That's the special thing, but we have no time and no possibility to describe it. So using that, you can classify all critical points in 2 dimensions. This is conformal field here because it's an infinite group of transformation. It gives all exhaustive information. In other dimensions, it is not. So every time it's a matter of good luck, or otherwise you have to sit down in your computer and do all the calculations numerically. But anyway, this is the idea. Many things have been done. In the remaining part of our lectures, we will discuss a few solvable cases. Some of them will be more or less trivial, like one-dimensionalizing model. And there is a non-trivial demonstration how RG works. You can do it by yourself. The RG, normalization group. And you will find out how and why it brings you to the right result, the correct result. And the second, much less trivial problem will be a 2-dimensional Gaussian model with only gradient term. And we will do very interesting calculations there. Very interesting physics will be found there. It will be the end of all lectures. So please try to solve the problems in the remaining parts of it. There is an overlap between the scale invariance in the main text and the extra text that I sent to you. But in most cases, there are problems there. Start solving them, and let us do it. Let us make it the following way. Today we have Friday. By next Friday, 1 week, try to solve as much as you can. That's because the better you perform, the easier will be the final exam. I don't know how you are aware or not, but to me, an exam is not a singular case when something dramatic has to be decided. It's a kind of one of the events in the whole sequences, right? The number one is the lecture. I talk to you, sometimes you talk to me, even though I would like you to talk more frequently to me than you do. But nevertheless, I can see some response. The second is the first homework, which I'm not very much impressed with, to be honest. And you perhaps know why. So I expect you to perform better than you did for the first assignment. Don't hesitate to come to visit me.
So starting next week.
Yes, I mean the main text, which is here, the main text. It also contains the discussion of how it's called, scaling properties or things like that. Don't touch so far. You will never touch upon one-dimensionalizing model and
The issue of transforming exponential.
yeah. So everything is up to your will. You can start reading whatever it's written here without waiting me to explain to you what is there. Or you may follow me and then start doing things after I have explained during the lecture. It's up to you. It's commutes. I'm not urging you to do everything right now. But you have already acquired some piece of knowledge, right? Jeff, please try to solve what is written in this extra piece of lecture notes. There are a few problems there. There are. Even though we'll be dealing with them with some detail later on, but At least you can write